Optimization. This is one of the biggest applications of what we've been learning. Let's say we were asked to build gutters to put around a house. You know, gutters are a shallow trough underneath the roof, catches rainwater. Notice there's not a lot around this area because the leaf buildup. But we want to make sure that the gutter is designed to hold a maximum amount of water. It protects the foundation. So let's say we have a large roll of sheet metal, measures 24 inches wide, and the length is sufficiently large enough to make gutters to go around the whole house. So that's why it doesn't stop, because it keeps going all the way around the house. And we can pick our different methods. We want to find the one that's going to give us the most water contained. Option A, we can fold it up directly in the middle and make a triangular prism. Option B, we can fold it up on two sides and make more of a trapezoidal. Or we can fold it up into a rectangle to create kind of a rectangular prism, as you see on the next side. Or what if we rounded it out and made a semicircular prism? Which one out of these four options would be the best for maximizing the volume of water held by the gutter? And how would you know which one's going to be the best? So to figure out which one is best, we're thinking about volume that they can hold, right? Because we want them to hold the maximum amount of water. So let's go back to page 57. A triangular prism. Now they all are going to have the same length because they're going around the house. So when we're talking about volume, of course, volume is the area of the base times the length. Now remember, this was 24 inches wide, so 24 went around here and here. So that would be 12 and 12, right? I'm actually going to leave this part of it for you. Which one do you think is going to be the best design? And sketch a picture of that exact design using the dimensions. Remember, we've got 24 inches of material. So around here, that'd be 24 going around here. 24 going around three sides here. Figuring out which one is actually going to optimize our water holder, capture is kind of an interesting problem to look at. Now, let's just look at some of the algebraic functions and optimizing these real-world situations. We're going to start by focusing on maximums because we'll maximize the volume in that first problem. And finding minimum values is nearly identical, so very similar technique. What we want to do is find the x values that will maximize the function. So notice on this one, we have a parabola, and the maximum of that function is at x equals 4. What would the derivative be at that point? Well, it's at the top. Slope of the tangent line would be 0. So f prime of 4 is 0. Now, what about the next situation? Well, the maximum value is not a vertex. it is actually the highest point when we're looking from 0 to 10. So here, it's the x value of 0. Now, what is the slope at that point? Well, that's a little bit different because this is not a parabola. It's not the top of a hill. That is actually an end point, but we could still find the derivative. The derivative would be the slope at that point. So rise over run, we're going from 0.9 to 4.5. So that's down 4 over 4, which means we have a slope of -1. On this one, from 0 to 10, so it starts at 0, 0 and goes up to 10, 5. That's the highest point on that interval. And the slope there, yeah, so up 5 over 10 is 1/2. What about here? What would be the maximum? Well, we actually have two places, right, that have a maximum value. But if I were actually trying to find a maximum, this would be the absolute maximum. X equals, it looks like 6.87. And what is the derivative at that point? Well, slope of the tangent line is 0. Ooh, interesting function. We have a little cusp up there at x equals 5. That is the maximum value. What is the derivative at that point? Well, the derivative does not exist at that point because that's a sharp turn. So there are three ways for a continuous function to achieve a maximum value. Notice that we had times where it was an endpoint, and then we had times when the derivative was 0, and then we had a time where we have that sharp turn. So this would be an absolute maximum. And this one, we had a sharp turn. So to optimize a function algebraically, we need to find the critical points. Those points where the derivative equals 0 or where it doesn't exist. And then argue which point will maximize or minimize the function depending on what we're asked to do. If the endpoints exist, see which of the endpoints or critical points gives the largest or smallest value. If we do not have endpoints, we need to see which critical point would yield a relative maximum or a relative minimum. By discussing concavity is another option to talk about that second derivative. So what if we had this function and we needed to find the critical points of the function? So we want to find when our function equals, when the derivative equals 0. So let's find that first derivative. And then the derivative of a constant is 0. So we want to set that equal to 0. Can factor out a -4x. Gives me x squared minus 10 equals 0. So we have when x equals 0, or when x squared equals 10, which would be Normally we'd say plus or minus 10, but square root of 10. Positive square root of 10 would be 3 and a little bit, which is in this interval. Negative square root of 10 is not in that interval, because that'd be negative 3 and a little bit. So these are the x values we want to check. Now, why do we need to check negative 2 and 4? Well, those would be the endpoints of the interval. Why would we need to check 0 and square root of 10? Because those are critical values. And what do we mean that we want to check to see which ones are maximums and minimums? That means we want to check what the y value, or f of x, is at each of these x values. So we need to plug it in. So for the sake of time, we can use our calculator. Now, to make sure everybody knows how they could use the calculator to check these points, now we're trying to find the y values for each of these. Now I know when I look at the graph, I'm gonna be able to see which ones are the maximums, but we want, on your test, you want to actually write down the actual f of x. So f of negative 2 and so forth. Now there's two ways you can do that. You can go to the graph and trace it, or we can plug those values in manually. Or we can do y1 of negative 2, and it gives me the f of x that goes with that. y1 of 4. Ooh, notice our endpoints are both 0. And if we look at the graph, we can also see this. Well, actually, it's hard to see because this graph is very, very tall. We'd have to play with our window to see it because it's going all the way up to 36 and it's all the way down to negative 64. That's really out of our window. So which one is the maximum? The maximum value of f of x is 36. That's the maximum value. Now, it occurs when x is square root of 10. Now, what if those endpoints weren't included? Well, we're given the same function, so we already know what our critical points were. It was x equals 0 and x equals the square root of 10. Now, the other way to check for whether it's a maximum or a minimum value is to check the second derivative. So we had that the first derivative was negative 4x cubed plus 40x. And the second derivative would be negative 12x squared plus 40. So if I plug in 0, I'd get 0 plus 40, that's 40. That means it's concave up. The second derivative at square root of 10. Squaring a square root, that would give me 10 back. Negative 120 plus 40 is negative 80. That's concave down. The maximum value is still 36 because the square root of 10 gives us a concave down, which if we look at the graph on the back page, you can see it. Concave down means we have a maximum there, and that 0, negative 64 would actually have been a minimum. Now let's look at some real-world problems. A farmer has 600 meters of fencing to fence in 3 identical adjacent rectangular pastures. A long stone wall is used for one side of each rectangle. Find the maximum overall areas if each rectangle must be at least 40 meters wide and at least 80 meters long. So we're trying to maximize area. Let's think about a sketch of the situation. So we've got a stone wall. And we're having 3 identical adjacent pastures. This is a small sketch. Adjacent. Now the length would be these, right? And each rectangle has its own width. And I'll put that here. Width, length, length, length. So the area of all 3, well, that'd be 3 times length times width. But let's think about how we can write this in one variable. So if we think about the width, if we take all 3 widths plus all 4 lengths, that's supposed to be 600 meters, right? Okay. Let's solve for W. Solve for L. 600 divided by 4, that'd be 150 minus 3/4 the width. So now I've got an expression for the length in terms of the width, so that I can write that the area in terms of width would be the width times 150 minus 3/4 the width. It's going to be a lot easier to work with if we put it in standard form. Now we also have some stipulations there. The rectangle must be at least 40 meters wide. And the length has to be at least 80. So this has to be at least 80. At least greater than or equal to 80. That'd be 280 over 3. Do the endpoints make sense? Could we have a width of 40? Well, we want at least that. And could we have a width of 280 divided by 3, which is like 90 something? It could work. Now, what other points do we need to check? Well, we need to check when the derivative is 0. So let's look at that first derivative. That'd be 150 minus 3/2 W. And we want to know when that equals 0. Multiply both sides by 2/3. And we get 2/3 of 150. It's 50 times 2, that's 100. So we have our points to check at x and at f of x. We have 40 and 280 over 3, which are my endpoints. And then we also have 100 to check. And that's a critical value. So what happens if I plug those back in to my original function? Well, if I plug in 40, and I'm just going to do it from this screen, 40 times 150 minus 3/4 times 40, I get 4,800. And then what about 100? Three-fourths. Whoops. Now the problem comes into what was our maximum value for our width? Was 280 divided by 3, which is 93 feet. So that 100 is actually out of this range. So the maximum we can make with those limitations is 7,466. An open rectangular box with a square base is made from 48 square feet of material. So a sketch of that. We've got an open box. And it said it was a square base. So this side and this side are the same, right? Now let's think about what that would be unfolded. We've got these squares cut out, right? And those are the same as that height, right? Each of these little squares cut out would be height by height, right? Height by height. Height by height. Height by height. So if we looked at it as a big picture, the area, if those little corners weren't cut out, would be x plus 2h's squared. But we're subtracting out 4 of those h's. And we want that square footage to be 48 square feet of material. Now we're supposed to only have one variable in our volume formula, which, our volume would be x times x, which times the height. But we need it to only have one variable. So let's see, x plus 2h squared would be x squared plus 2 times x times 2h, which would be 4hx, plus 2h squared would be 4h squared minus 4h squared equals 48. Oh, that's cool. X squared plus 4hx equals 48. Which variable would be easiest to isolate so that we can get our function only in one variable? Well, h would actually be the easiest. So now I have an expression for h, which I can plug back into here. Now, we could leave it like that, but that's just crazy. Sorry. X goes into x squared, gives me an x. So I have 48x minus x cubed divided by 4. 12x minus 1/4 x cubed. Do the endpoints make sense? Well, one of the endpoints would be 0. Does that make sense? Not really. The other endpoint would actually be the other place where the volume is 0, which doesn't make much sense at all. No, those would not give me a maximum volume. So the only place I really need to check is when the derivative is 0. So 12 minus 3/4 x squared, we want to know when that equals 0. Or when 12 equals 3/4 x squared, multiplied by 4/3, so when x is 4. Now what is the maximum volume? Well, first we need to make sure that 4 is a maximum. How can I check that? Oh, I could check the second derivative. That'd be negative 3/2 x. Oh, it's going to be negative when I plug in 4. So the second derivative at 4 is less than 0, which means we're concave down, which means 4 definitely will give us our maximum volume. So I just need to go find out what that is. 12 times 4 minus 1/4, 4 cubed. 4 cubed is 64. 64 divided by 4 is 16, so 48 minus 16 is 32. So the maximum volume is 32 cubic feet. Now, if we go back to that design of the trough, and I don't know which one you picked, the most widely used design is actually the trapezoidal prism. So we assume that it's created by bending up 1/3 of the sheet on each side through some kind of angle. Now we need to know what angle would maximize the volume of rainwater. So I'm coming back to this, the gutter with the trapezoidal bend in it, and we're going to see if we can, how we can figure out what would be the maximum. So we're really thinking about that maximum area, huh? What angle of bend would actually maximize the volume of water? So if we bent it up into 1/3, and let's see, what did we start with? We started with, wasn't it 24 inches of material? So this would be 8 inches, 8 inches, and 8 inches. Now, if we're maximizing the volume, we need to maximize the area of this figure. So how can we figure out what angle would actually maximize that? Let's just call that height for fun. Now, how does that height relate to that angle? Well, it's opposite, and we know the hypotenuse, right? So the sine of that angle would give me h over 8. In other words, h is going to be 8 sine theta. This little piece would be 8 cosine theta. Now, why is that piece going to be important to know? Well, because I need to know the length of that entire base. Remember, the area of a trapezoid is 1/2 base 1 plus base 2 times the height. Well, if that little piece is 8 cosine theta, then this one is 8 cosine theta. This entire base is 8 plus 8 cosine theta plus 8 cosine theta. The smaller base was 8 plus 8 plus 16 cosine theta, and the height is sine theta. Could you figure out what angle that needs to be at?